In this video, I'm going to talk about the concept of permanence and how we can value impermanent sequestration. But let me start by talking a little bit about why an increase in carbon dioxide levels was bad for the world. The Earth is surrounded by a very thin skin of an atmosphere, and the sun's rays come into the Earth, and when they get reflected back, they are reflected at a longer wavelength, and this longer wavelength is absorbed by the carbon dioxide in the atmosphere, and this causes heating. And so, of course, if there's no carbon dioxide or no greenhouse gases, that would be terrible because the Earth would be very cold. But in fact, a certain amount of carbon dioxide is just right for us to keep the Earth nice and warm. But if you have too much carbon dioxide, then it gets very hot. And when this happens, then we get heat waves, we get melting glaciers and polar ice caps, and we get flooding and all sorts of problems. So an increase in carbon dioxide beyond the historical levels causes a lot of economic damage. Now, the other problem we have is that any emission of carbon dioxide into the atmosphere lasts in the atmosphere for quite a long time, about 300 to 500 years. So if you're taking a plane and going on a trip somewhere, then the carbon dioxide emissions from the back of the plane are going to be staying in the atmosphere for this period of time, 300 to 500 years. And during that time, they're going to be causing economic damage. So what we'd like to do is to remove the carbon dioxide from the air. And what we can do is if we have this is the surface of the earth, there are often underground caverns such as this. And if we can install essentially a giant fan over here, we can suck the air into this and extract the carbon dioxide using some chemical filters and pump the carbon dioxide into the cavern. And when this happens, eventually the carbon dioxide forms calcium carbonate in the sides of the cavern, and this is chalk. And this is what they think of as permanent or geological sequestration. And the advantage of this is that that carbon dioxide that is in the air and would be causing damage for 300 to 500 years has now been converted into something which is not going to cause damage at all, and it's completely captured. Now, this is a great idea, and of course, we'd like to do all of this with all the excess carbon dioxide. But the problem is that it's very expensive. It's costs perhaps between 300 to 1,000 US dollars a ton to do this kind of capture. And these prices are coming down, but still they're quite expensive. So one might want to look for alternatives. What could you do instead? The one technology that everybody knows about and works really well is to plant a tree. So when a tree grows from a seedling, a little seedling into a tree, it's accumulating what we call biomass. And this biomass is made basically from carbon atoms. And so the atmosphere, which has CO2, is now being captured in the form of trunks and leaves and so on into this tree. And of course, if we have a lot of trees, we have a forest, then this forest is going to capture quite a bit of carbon dioxide in its biomass. Now, the biomass in the forest comes in two forms. It's the above ground, which you call above ground biomass, or AGB, and then the below ground biomass, which is in the form of the roots and so on, and also, of course, the fungi that grow in the forest and so on. But we really don't have very much idea of how this works or how much carbon is in there. So for my presentation today, I'm going to focus mostly on the above ground carbon, or AGB. Okay, so the problem with forests, which is a great idea to grow, but the problem with them is that they can be cut down, they can get disease, or they can have fires, or even windstorms, which can cause a lot of tree fall. And when the tree falls, the tree starts emitting carbon dioxide again as it decomposes. And so this causes a return of carbon dioxide back into the atmosphere. And so in that sense, the forest can be viewed as being impermanent. Now, compared to a geological sequestration that we saw over here, this is not so good because we have over here in this case a permanent sequestration, and here we have impermanent sequestration. And so the question is, what is the value of an impermanent sequestration? Is there any value at all? We can go about it understanding the value in a couple of different ways. And one way of doing things is to take the forest and set aside a certain fraction of it, which we call the buffer area. And so we are going to say that this part of the forest is always sequestering carbon. And if there is a fire or a flood, a fire or a windstorm in some part of the forest, we'll just compensate for that from the buffer area, which is over here. So this is equivalently balanced over here. And so if you take the overall land over here, which is both the non-buffer area and the buffer area, then that overall area can be thought to be being more permanent. But this has some problems in accounting because the buffer area is only there during the duration of the carbon sequestration project itself. Given that a forest could be impermanent, is there a way for us to find out what the value of the impermanent sequestration is? And to understand that, we will use the concept called the social cost of carbon. And this was a concept developed by Professor Nordhaus in the mid 90s, for which he recently won the Nobel Prize in Economics. It's a fundamental concept, so let's see what it is. The idea is that the emissions of carbon dioxide into the atmosphere cause economic damage. We already saw this, but we can actually value this damage. We can compute the total value of the economic damage, and by doing so, we can attribute the damage caused by a single additional ton of carbon dioxide in the atmosphere. So let's take an example. Let's say that we emit 1 ton of CO2 in the atmosphere in the year 2022. So this ton of CO2 is going to be added to the existing amount of carbon dioxide in the atmosphere. And based on this, it's going to cause some amount of economic damage in the years to come. So in 2022, there'd be some damage, there'd be some damage in the year 2023, etc. And depending on how we model the evolution of carbon dioxide into the atmosphere, we're going to get a certain amount of future expected damage according to the carbon emission pathways computed by the IPCC. So based on the IPCC protocols, we can expect a certain amount of damage into the future for a particular pathway. So for example, the so-called business as usual pathway, which is RCP 8.5, is assuming that we have a huge amount of damage into the future. And of course, if we have much lower emissions, which is going to be like corresponding to 1.5 degrees, then we will have less damage going into the future. We probably have a decline in damage. But at any rate, for each year, we have a certain amount of damage we can expect based on the IPCC analysis. So if we take a single extra ton released in 2022 of this total emissions, we'll just say here's some single emissions. That little bit of emission, that 1 ton of emissions, is going to be responsible for a certain amount of damage in each of these years. And this amount of damage in each of these years can be estimated based on the IPCC pathways. And so what we have then is that we can say that this 1 ton may cause, let us say, $200 of damage in the year 2022. It causes another $225 in 2023, and so on. And so we can sum that all up over the next 300 years to 23, 22 for the next 300 years. And that'll give us quite a large amount of money. But one thing we need to note is that if there's a damage happening in the year, let's say 2100, and it's, I don't know, let's say it's $2,000 in damage 2100, that's into the future. And so we want to discount it to the current time. And by discount, I mean that the present value of a future damage is given by the discount rate. And so if we have a discount rate of, let's say, delta, then we take a future damage and we divided by 1 plus delta to the time between then and now. So this is future minus now, and we take the damage, and that gives us the discounted rate from here. So, for example, if the damage were $2,000, and that is in the year 2100, that 2100 is 78 years from now, and let's say delta is 2.5%, then we'll take the $2,000 divided by 1 plus 0.025, that's your 2.5%, and to the power 78, and that will give us some value here, which will of course be quite a lot less than $2,000. Let's say it's $20. That's of course probably not right, but anyway, that's the number we're looking at. And so this tells us how to take all of these future values and then discount them by delta to tell us the current value. And that current value is going to be the social cost of carbon. In other words, what we're saying is that the emission of a single ton of carbon in 2022, we can compute the cost in discounted economic damage. And that is the social cost of carbon in the year 2022 for 1 ton. Now, if you release, let's say, 200 tons in the year 2022, then the damage is going to be linearly increasing. So it's going to be 200 times SCC 2022. And since it depends on delta, it's probably a good idea to put delta as a parameter so that we can keep track of that. Okay, so far so good. We just talked about the damage and the social cost of carbon, but what is the benefit of impermanent sequestration? And to discuss that, I'm going to use this following little cartoon diagram. So let's say that we have time on this axis, and over here I have a sequestration, and then here I have release. So let's say that we sequestered in the year 2022 20 tons of carbon. What is the value of that? Well, if you had 20 tons that were released in 2022, then we would have the damage of 20 times SCC 2022 with some parameter delta. So if we were to sequester it, the benefit is going to be exactly the opposite. So that's the benefit equals this. So that's good. And now I want to see what is the damage caused by impermanence. So we have this forest. Let's say we have forest which is sequestering 20 tons in 2022, and perhaps we anticipate that there is going to be some amount of release in future years because of disease or because of fire or because of windstorms or because of human activities. And this we call the release schedule. So this is the expected release of the sequestered carbon in 2022 in future years. So what would be the damage caused by this release? Well, we know how to do that. Let's say that we denote this to be the year Y, and then we say that this release is happening in some other year. So let's call this Y0, this happens in Y1. Now, we want to know the social cost of carbon in Y1 with some parameter delta, and the amount of release we have is going to be this one over here. Let's call that R1 release in Y1, R2 release in Y2, R3 release in Y3. So we're going to have R1 tons released in Y1, and that's going to have this cost. And then, of course, this is discounted because it is in the future, and the discount rate is 1 plus delta to raise to the power Y1 minus Y0. And so this is going to be the damage caused by the release in the year Y1. And similarly, we can compute the damage in the year Y2 to be just the same R2 SCC Y2 with this parameter delta. And that's SCC delta. In addition, we are discounting that to the current time to 1 plus delta to Y2 minus Y0 and so on. And so you can see that we can actually create a very simple summation which sums up all the damages in the years y1, etc., all the damages over yi and over I, and this is going to give us the net damage. And so we now know the net benefit. That net benefit was over here. We had the net benefit was this one over here, 20 tons times SCC 2022 delta, and we know the net damage over here due to that. And so we can compute the following, which is the net benefit of all this is going to be the benefit minus net damage. And this gives us the benefit that we can expect even after the damage is accounted for. And if you normalize it by dividing it by the benefit, we get a value we call the equivalent permanence. And the reason we call it that is because if we take a fully permanent sequestration, such as in a cavern underground, then it will have a net damage of zero because it has no release at all in every year. And then the equivalent permanence is going to be equal to 1. On the other hand, if you have a forest that goes up in flames immediately after sequestration, so it has sequestration and then the forest goes up in flames, then what's going to happen is that the damage equals the benefit. Whatever it's sequestered is going to be damaged, which implies that the equivalent permanence equals zero. And so in between, when you have impermanence that lasts an intermediate period of time, we've had equivalent permanence, which lies in the range 0 to 1. And you can view equivalent permanence as being essentially the value of the impermanent sequestration. So that's basically the value that we use in our work.